Hello everyone, I'm Yu Qianfu from Fudan University. I'm delighted to introduce our work for CVPR 2023. In this work, we propose a mental style adversarial training method for cross-domain future learning, which termed as StyleAdv. Cross-domain future learning transfers knowledge from source data with sufficient examples to novel target data with few labeled examples. Note that the source and target data have disjoint class sets and they also belong to different domains. Below show the existing benchmarks for cross-domain future learning. We can observe that there is a huge domain gap between the source and target data. Thus, critically, cross-domain future learning aims at improving future learning models across different domains. According to the data used for training, we roughly group existing cross-domain future learning methods into three types. Among them, the single source-based cross-domain future learning, which only has a single source data for training, is the most basic and also challenging setting. Thus, in this paper, we tackle the cross-domain future learning with only a single source data. Before I introduce our method, I would like to share why we tackle cross-domain future learning from the perspective of style augmentation. As shown in these images, we notice that obvious facial style shift exists between these images collected from different domains. Since single-source cross-domain future learning assumes that we cannot access to the target data during training, we thus wondering, could we just span the style distributions of the source data to narrow such gap? As for how to achieve the style augmentation, our previous work with SN proposed to randomly swap styles of between two source images, like this. Empirically, we show that with SN is effective. Such a naive generation method suffers from two limitations. The first is that the swap operation makes the styles always be limited to the real style set of the source data set. The second is that the limited real styles first lead to the generated styles are too easy to run. Thus, for StyleAdv, a natural question is that whether we can synthesize both virtual and hard styles for learning a more robust cross-domain future learning models. We then surprisingly found that the attacking technique could meet our needs for generating such virtual and hard styles. Inspired by but different from the classical attack method, we propose a novel style attack method. As shown in this left figure, classical attack such as FGSM attacks the image pixels by adding side gradients with respect to the pixels. By contrast, rather than attacking the image pixels, we first extract the style which is represented in the form of min and std, and then we attack the style in the similar way. That is, we add the side gradient with respect to the min and std to the clean original style. In this way, we form the adversarial styles. Since it is achieved by attacking, the generated adversarial styles are naturally both virtual and hard. To improve the style attacking method, we first made several improvements. Firstly, to attack styles at multiple feature maps, the most simple and direct way is to attack these feature maps individually. However, this may lead to the inconsistency between the attacking signals. Thus, we propose to attack in a progressive manner. Concretely, as shown in this animation, the attacking signals of the current block is accumulated by the adversarial styles from the previous blocks. Besides, in order to increase the diversity of the generated styles, we propose to randomly select the attacking ratio from a list rather than using a fixed one. This shows the whole framework of StyleAdv. Overall, StyleAdv plays a min-max gain under the adversarial training paradigm. The inner loop synthesizes adversarial styles, increasing the training loss, while the out loop optimizes the network, decreasing the training loss. Specifically, given a source episode as input, we first forward it into the network, and also we extract the clean styles in this process. Then we perform the style adversary the style adversary attacking using our aforementioned attacking method. For the out loop, we request our model to classify both the clean styles and the adversary styles. By iteratively perform the in loop and the out loop, we gradually improve the robustness of the cross-domain feature learning models. This shows the comparison results with the SOTAs. We mainly highlight 2 points. The first is that whether with or without fine-tuning on the few labeled target supported images, our StyleAdv achieves the best result. Secondly, we also observe that whether taking the Resonant 10 or the VRT Small as the backbone, we outperform all the competitors by a large margin. To show the advantage of attacking on styles, we compare it with that attacking on the image pixels or features. Results show that attacking styles perform best. This supports our idea that the facial style shift is critical to tackle the domain gap issue for cross-domain feature learning. Besides, since we augment styles, we also compare our method with other style augmentation methods. For example, the mix style. Results show that our method is the most effective one. Besides, our StyleAdv can be easily used in a plug-and-play way. Here we show the result of building our StyleAdv upon RelationNet, GNN, FWT, and PNF. We found that we steadily, maybe we can observe all of these results. We found that we steadily improve the base models to a large extent. Finally, we also provide some visualization results. A figure shows that the swap based with SAN tends to change the overall look of the image, while our StyleAdv will first modify the areas that are keen to recognize the class labels. In B figure, the blue line indicates the loss generated by the original clean styles, while the pink indicates the loss generated by the style augmented data. We observe that the StyleAdv obviously increases the difficulty of each meta text, while WaveSN doesn't. The C figure shows that the StyleAdv extracts more distinguishable features than the WaveSN in the field of TSME. In conclusion, we propose a novel style adversary training method, StyleAdv, for cross-domain feature learning. To support the style generation, a novel style attack method is proposed. Also, our method is complementary to existing feature learning and cross-domain feature learning on both CNN and VRT backbones. Codes can be found here. That's all for my sharing. Thanks for your listening.